Hi, I'm actually recording now. I forgot to hit the start button for you kids who are there. So we're going to restart this video. Thanks for watching. I am kind of a dork, it appears to be. So yeah, we're going to start over and answer the questions here in a second. For those of you who are currently waiting for it to start, it will start soon. Oops. Okay, so those of you in the Google Doc know that I forgot to hit start, so the video will be starting shortly. For those of you who are in here, I will kind of start over again. I currently have a sick baby right now who is sleeping, so if she wakes up, I may have to leave for a few minutes to come back, to go put her back down, and then I'll come back to the video. So if you see me just up and leave, I'll give you a heads up that, hey, I'll be right back. So I apologize about that. It's probably going to be a little bit of time in between when I answer questions because I'm going to go back and forth between what I'm writing on the screen and the Google Doc for the questions and try and organize them so I can answer your questions in as efficient manner as possible. So I hope that you guys are able to see right now what's going on. Let me check and see what YouTube has up. Broadcasting yet? Oh, yep, it is. Okay, perfect. So I'm going to go through the questions that I said I already answered, and I am going to answer them again. So a couple of things, if you are in the Google Doc, words you do not need to know. You do not need to know oxidizing and reducing agent. Those were things that we decided not to teach this year that we forgot to take off the review packet, so we apologize for that. So you do not need to know those words, oxidizing or reducing agent. You also do not need to know any of the stuff on batteries. We took that out as well. So anything that deals with batteries, corrosion, anything in the chapters, if you're reading the textbook about those two things, you do not need to know for the test. On the test, in terms of a drawing, if it's going to be acidic or basic, what's happening around the electrodes with the water and the reaction. What we would do on the test is we would definitely give you some context clues if you needed them. So we would talk about maybe an indicator turning a color that you know is acidic, maybe such as universal indicator turning red, or if it's basic, universal indicator turning purple. And if you're having a difficult time knowing what reaction to use, you get the reduction potentials chart on the test. So that table in your textbook that we've been using for a lot of the homework to calculate E cell, you get that on the test. We provide that to you. So if you know it's producing a basic pH, then you can go ahead and look at that reduction potentials chart and figure out, okay, which one is the water reaction making a basic pH, because I know this is the reaction that's happening at that electrode. So you can definitely use that reduction potentials chart to your advantage for those harder equations where you may not be 100% certain of what's going on. So I would definitely look at that chart because it's going to give you a lot of free answers if you know how to use it correctly. If you have any more specific questions about that, please stop by in the morning because I can do a much better job of kind of giving you those hints in person than just via a video broadcast. The next question I got was about redox reaction balancing and whether or not we will tell you if it's acidic or basic. Unless it's blatantly obvious, meaning on the reactant side, you have something that has H's in front, which means it's an acid, or you have something with OH minuses in the back, which means it's basic, we would have to tell you. So if you think about the homework half sheet we had when we did balancing reactions, a few of the things did not have spectator ions in them. So it was just a couple of ions on the reactant side and a couple of ions on the product side, and there's no way to tell if it's acidic or basic. That would be a situation where we would absolutely tell you this is in an acidic solution, so you know that you're just using H pluses, or this is in a basic solution, so you're using OH minuses. So we would definitely tell you if it was acidic or basic if it was not obvious. And remember, if you're ever uncertain on a question on a test, you can always ask us. The worst thing we can say is, I'm sorry, I really can't answer that. But odds are we can either rephrase something or help you better understand the meaning of a question if you just ask us a simple question during the test. So I'm going to get into these review sheet questions that people have. I'm just going to come down to the document and see if anyone has added. Nope, doesn't look like any other review sheet questions have been added. So I'm going to go ahead and answer these starting at 8:51. So the first question I'm asked about is question number 8. So if you have your review sheet handy, question number 8 says, the following equations are used to make an electrolytic cell. What occurs at the anode? So the two equations you have. Oh, no, I want this guy here. So the two equations you have, I have to screen share this with you. Oh my gosh, my brain is broken right now. Okay, share. All right, so the two equations you have on that sheet are excuse me, Br2, that's in the liquid, plus 2 electrons, going to 2Br minus 1. And the second equation you have is Na plus, that's aqueous, going plus an electron, going to solid Na. So what you would need to do is you would need to go ahead and you would need to use the reduction potentials chart to your advantage here, because it says which of these would occur at the anode, and the big hint here is it says it's electrolytic. So if you look at the reduction potentials chart that you have in your textbook, are the one that will be provided for on the test. On the reduction potentials chart, this one has the more positive number, which means this is the one that wants to reduce in a normal cell, which means this would be the one that would want to oxidize in a normal cell. But because this is an electrolytic situation, what we want to do is we want to make the things go the direction that they don't want to go. So since we're going to hook it up to a battery, that's going to be what drives the electron movement. So in an electrolytic cell, the guy that normally wants to reduce is what's going to happen at the anode. And the guy that wants to oxidize is going to be what happens at the cathode. So that is how I know that equation number 1 is going to be the one that occurs at the anode. So it's just the opposite of what would occur in a normal voltaic cell. So I hope that question helped you. All right, so let's go back to the questions. All right, the next question we have is, how do I know what is being oxidized and what is being, oh, sorry, shoot. I skipped number 4. I didn't even do number 4. Ay. Well, Mrs. Etnyre, you struggle right now. I blame the fact that I was so sick today. All right, so that was number 8. Let me number this guy here. Let's go back to number 4. All right, so number 4 says, investigate the following. We've got 2Sr plus O2 going to SRO. And it says, we want to complete the following sentence. Blank is reduced and blank is oxidized. So we have to go ahead and assign oxidation numbers to this guy here. So SRO are free elements, and free elements get the oxidation number of 0. And then SRO is an ionic compound, so we use the periodic table to determine the charges for those pieces. So we know O is the -2 ion, and SR is in column 2, so it's a +2 ion. So remember, oxidation means we're giving away electrons, so our number is going to go up. So our SR is going to be what's oxidized in the reaction. Our O is going from 0 to -2. Its number is going down, so that's going to be what's reduced in the redox reaction. So for the sentence, O is reduced and SR is oxidized. And that is the question answer to number 4. The next on my list is number 9. Number 9. All right, number 9 says, the following equations are used in a galvanic cell. Which reaction occurs at the anode? Again, this is going back to that reduction potentials chart. So the first guy you have is you have CD2 plus 2 electrons going to CD solid. And the second one you've got is MnO4, 2 minus, plus 8H plus, going to, plus 5 electrons, going to Mn2 plus 4 H2O. So if you pull up the actual reduction potential chart, which I'm going to do on this problem, I can't do it on my computer because I did not have access to that. So I have it on my phone because, we all take pictures of things today. So if I look at my reduction potential chart and I look up the reduction potential voltage for these things, this reaction is plus 1.507 volts as a reduction. And the other one, CD. Of course, when you want to find it, you can't find it. Why would you be able to do that? It's going to be like you guys on the test. It says, Etnyre, I can't find the CD. I can't. Oh, wait, there it is. Negative 0.4030. So these are the reduction potential numbers that are actually provided from that chart. So what these reduction potentials tell us is the likelihood of something to happen as a reduction. So the more positive you are, the more you want to reduce. The more negative you are, the more you want to oxidize. So in this situation, we know based off the reduction potentials that this negative number would be the oxidation and the positive number would be the reduction. Now, all we have to do is ask ourselves, is this for an electrolytic or a voltaic cell? So if you read number 9, it says a galvanic cell, which is just another word for voltaic cell. So this means it's a cell where we want to let the things do what they want to do. So in this case, because this is a voltaic, this guy would be our anode, because we want to let him oxidize, and this guy would be our cathode because we want to let him reduce. So equation number 1 is going to be the guy that happens at the anode. Where if we go back to the question I answered just before this, the only difference is this one was electrolytic. So in an electrolytic cell, you would do the opposite of what it wants to do. In a voltaic cell, you let it do what it wants to do. All right, onward with the review questions. Number 11. Number 11 says the oxidation number of N and NH3 is -3. This means mark all that apply. So the first thing we want to do is we want to look at this compound. NH3 we know is a covalent compound, so it does not make ions. It takes on a -3 characteristic because it's more electronegative than the H's. The H's take on a +1 characteristic because they're less electronegative. So that means all these electrons are being pulled towards the N, and the N is feeling more of their love, which is why it's becoming slightly negative, and the H's are becoming slightly positive. So this is the quote-unquote transfer of electrons because the N is pulling it closer to them. So if we look at the options that we have, option A says the nitrogen has a -3 charge. That is not true. This is a covalent compound. It does not make ionic charge, so it does not take on a -3 charge. It takes on a -3 oxidation number because it's pulling 3 electrons closer to its nucleus. B says, oh, I don't know how I did that. That was pretty fancy pants. I just hit something on the button and the page moved. Sorry about that. Letter B says hydrogen does not have any electrons around it. That is also not true because these lines indicate a covalent sharing of electrons, meaning that the hydrogen does still feel some of this electron love. It just doesn't spend as much time around the hydrogen nucleus as it does the nitrogen nucleus. Option C says the nitrogen is partially negative but does not have a charge, and as we saw in this picture, that is completely true. This does take on a partial negative character, while your H's take on a partial positive character. D says this is an ionic compound, which we know it's not true. And then E says -3 is a number we assign to N so we can track electrons. That is absolutely what we're doing. We're just using this to figure out right now it's pulling 3 electrons from hydrogen closer to its nucleus. If this reacts with something else, what happens to those electrons? Do they remain with the nitrogen? Do they go someplace else and make a different covalent bond? So this is simply a number that we use to figure out where those electrons are going. All right, I hope that one helped with that one. Now our next one is question 12. Question 12. All right, so number 12 says, what are the products of the following unbalanced reaction? So we've got Ni plus, or sorry, NiCl2 plus Na. So what we need to do is we need to do the single replacement reaction. So for those of you that have me as your teacher and don't have Mrs. Staub, I talk about this as the new reaction because I hope this never happens to you. I got left at homecoming my junior year by my date. So I was in a compound and then I ended up by myself. My mom had to come get me and it was a very, very sad day in Mrs. Etnyre's life. However, it helps me teach single replacement reactions. So how we figure out what the products are is first we want to check our activity series and see if sodium is above nickel. And when you look at your activity series, you will see that sodium is absolutely above nickel, so this would be a regular spontaneous reaction. So when you do single replacement, you switch with the piece that's like you. So because sodium and nickel are both metals, that's who's going to switch. So our sodium becomes part of our chlorine compound, and I know it's NaCl because sodium makes a +1 ion and Cl makes a -1 ion. That means that the nickel is going to get kicked out on its own. So I end up with nickel by itself as my other product, which is how I know the answers to that question are C and D. All right, number 14. On to my next page. Oh, I could probably fit 14 in here. All right, 14 talks about the characteristics of both electrolytic and voltaic cells. So if we think just generally about electrolytic and voltaic cells, if I just kind of draw just a quick general sketch. Voltaic cells, we know, have 2 beakers. The electrodes are connected by a wire. They have a salt bridge or a porous disc, and they have some solutions in them. Electrolytic cells contain one beaker. They still have electrodes. There is a battery. Oh, I made two positive sides to a battery. That does not exist. Excuse me. Oop, got a little overzealous with my erasing. There's a battery that those electrodes are hooked up to, and that's what drives the electron flow. The positive side of the battery defines this as the anode. The negative side defines this as the cathode. For this, it doesn't really matter what I label. I'm just going to call this anode. I'm just going to call this cathode. Your electron flow is always anode to cathode in both electrolytic and voltaic cells. All right, so just our general schematic, what we have going on here. So if we look at some characteristics that are common to both, they both have electrodes present, which is why A is an option. B says the battery is required to make the cell work properly. Batteries are only need for electrolytic cells because these things are non-spontaneous, so that battery is needed to drive the electrons to move in the direction we want them to move, not the directions they normally want to go. So that battery allows us to drive which way the electrons go. C says a salt bridge must be present to make the cell work. That is only true of your voltaic cells. We need that salt bridge to make sure that these solutions remain electrically neutral. So the only one that needs a salt bridge would be your your voltaic cell. And D says a wire must connect the anode to the cathode in order for the cell to work. And that is true of both of these cells. In order for us to get the electrons to actually move from the oxidation to reduction in a voltaic cell, we have to connect our metals with a wire, which some of you experienced in the Lime lab. In the electrolytic cell, if we don't hook up the electrodes to the battery, nothing's going to happen within the solution that we want to happen anyways. So we need those wires to connect the anode to the battery and then the cathode to the battery to drive the electron flow how we want. So that is why A and D are the correct answers. All right. I have please go back to question 12. For whoever's typing the Google Doc right now, it says, why wouldn't Ni be Ni2 plus? And also, can you talk more about how you know the reaction will occur because the Ni is above the Na in the activity series? I can absolutely go back and expand on that answer a little bit more. So I'm going to go back and hit number 12 a little bit more here. When you're doing a single replacement reaction, your pieces literally switch spots and become exactly like the person they're kicking out. So if we look at this compound NiCl2, I know my nickel has a positive charge and my Cl has a negative charge. Because sodium is a metal, it takes on a positive charge, so it becomes a positive ion in that compound. The reason the nickel does not become an ion is because it is actually getting reduced back to a solid metal. So if we think about the half reaction for this, you're starting with your nickel 2 plus ion, and the only thing it could do is take in electrons because it's in an ionic form. So it is being reduced into solid nickel, which is why it's not written as a nickel 2 plus, because in order for these two pieces to switch places, sodium needs to lose electrons to the nickel in order to take its spot with chlorine. So the nickel takes in those electrons from the sodium to turn into a solid piece. That's why if you think about the demo that both Mrs. Staub and I did on the very first day of talking about voltaic cells, when we put that nail into the copper solution, the iron and the copper are literally exchanging electrons. So that iron was turning into ions in solution and the copper was turning into solid on the outside of that nail. It's also why in the electrolytic cell, we saw the copper form on that one electrode because it's actually taking the electrons to become a solid. So when you're doing these single replacement reactions for voltaic cells or any reaction for that matter that's going to be reducing a positive ion, you're always going to end up with that positive ion turning into a solid, no longer an ion on the other side. Now, how I know that this reaction is going to happen is based off activity series. I'm just going to kind of draw a generic activity series on here. So we know lithium's on the top, we know that gold and silver are on the bottom, and sodium is pretty close to lithium, and nickel's kind of down towards the middle of the activity series. So how I know that this is actually going to happen is this activity series is based on electronegativity. It's based on electron love. So the less electron love you have, the higher you are in the activity series. The more electron love you have, the lower you are in the activity series. So since we have low E love on the top, that means we want to give electrons away, which is why we oxidize, because we don't care about our electrons. We don't care that we keep them, we give them away. At the bottom, we have a high electron love. So we do want to keep them or take them from people, which is why we reduce. So how I can use this to figure out, hey, will this reaction actually take place, is the piece that wants to get rid of electrons, which will always be your solid metal, has to be above the piece that's aqueous in solution. That will always be the piece that's part of your compound. So because the sodium, which is by itself, which has the electrons to lose, is located higher on the activity series than the nickel that's in the compound that wants to take in the electrons, this would be a spontaneous reaction. It would be non-spontaneous if the sodium was a part of the compound and the nickel was by itself, because I have to be able to have my solid metal give the electrons away to the ion. And the only way that can take place is if solid metal has a lower electronegativity than the ion in the solution that it wants to react with. So I hope that answered it for you. I'm going to go back to that doc and ask if this is good or not, and if they want more explanation here. I believe that also answers the question down here. How do you know what's being accessed? Ooh, I just answered this one. Whoop. Answered 906. Okay. Okay, so I feel like I didn't get a comment back to that, so I think that might be good if that's okay or not. I'll come back to that doc in a second. All right, I've done 14, on to 18. All right, on to 18. All right, 18 says, the electrolysis of an aqueous sodium chloride solution using inert electrodes produces gaseous chlorine at one electrode. At the other electrode, gaseous hydrogen is produced, and the solution around the electrode becomes basic. Which of the following equations is the correct equation for the cathode half reaction of this electrolytic cell? So we kind of draw a picture about what this is telling us. I really like pictures in this chapter, so tomorrow when you're taking your test, if there's ever a question that you're like, oh my God, I can't keep all these words straight, just draw a picture. So if we break this down, we had a sodium chloride solution. So we had boop, boop, boop. We had Na and Cl plus minus in our solution. It was electrolysis, so I know that I've got this one solution hooked up to a battery. Do you like my drawing noises? I hope you can hear them. At one electrode, we had gaseous chlorine produced. So what that means is at one electrode, I had to have my chlorine come in, and I had to have bubbles produced of chlorine gas. I know that this is happening at the anode because if this is starting as a negative piece and going to an uncharged piece, the only way I can do that is by losing the electrons. So I know this has to be the reaction that's happening at my anode. It tells me at my other electrode, the solution becomes basic, which means I'm making OH minuses. So I can draw those in my picture. It tells me gaseous hydrogen is produced. So I know I'm getting some bubbles of H2 gas. And that's all it tells me. So I want to know what's happening at that electrode. I want to know what's happening at that cathode. So since I've already defined that, in order for my chlorine to turn into chlorine gas, it has to drop off electrons. I now know that my cathode reaction is going to be making my basic OH minus ions. So I know here it's going to be my 2H2O coming in and going into OH minus and H2 gas. An easy, excuse me, an easy cheat for this reaction is you have two things present. You've got Cl minus going to Cl2 gas, and then you've got water going to OH minus. What you can do is you can use your reduction potentials chart to figure out which one would normally want to oxidize and which one would normally want to reduce. Because since we have a battery, we're going to make it do the opposite. So since in this one, normally chlorine would want to reduce and this would normally want to oxidize, because I know it's electrolytic from the question, I know that this is going to be the one that would have to reduce in my solution. So you can use that reduction potentials chart as a quick cheat to figure out that, hey, this has to be the one that's happening at the cathode because it has a lower reduction potential than the chlorine. So I hope that makes a little bit of sense, and I hope that helps with that question there. All right, 18, 17, and 16 are up next. Let's go back to 17. Oh, that's not what I wanted to hit. Oh, man. Oh, man. My husband's probably just laughing at me in the other room right now because all I keep saying is, oh, man. Right. 17 says, how many moles of electrons are transferred? So we've got this reaction here. We've got 2Cr3 plus 3Cu going to 2Cr plus 3Cu2 plus. So tomorrow on your test, if there's ever a question that says, hey, how many moles of electrons are transferred? What you want to do is write 1/2 reaction, because 1/2 reaction is going to give you an idea of how much is happening as long as it's balanced. If it's not balanced, you want to balance it first and then write the half reactions. So I'm just going to do the Cr3 plus to Cr half reaction because that's going to help me see how many electrons are actually needed. So if I start with 2Cr3 plus, 2 times 3 is positive 6. So that means I know that this side has no charge. So in order for me to have no charge, 2 times 3 is positive 6. I need 6 negative electrons to make that reduction go. So because the 6 is the coefficient, that's how many moles of electrons I have happening, or I have moving. And to prove to you that it's 6 in the other half reaction, when 3 Cu's react into 3 Cu2 plus, again, 2 times 3 is 6, that's going to give off 6 electrons. So you can just write a half reaction for either the oxidation or the reduction and put the electrons in there and see how many moles of electrons are moving. So that's how you answer number 17. I believe number 16 was next. It was. All right, 16 says, under standard conditions, what is the standard cell potential of the cell? So we have this cell here. We've got CD to CD2 plus. And then we've got Cu to Cu, Cu2 plus to Cu. So if I'm going to steal this number, because I already looked it up, negative 0.0430. So for my reduction potentials chart, I know the reduction potential of CD is CD to CD2 plus is negative 0.0430. So I'm going to look at my copper 2 plus to solid copper. And from your reduction potentials chart, that number is, and you'll have to excuse me, this may not be exactly perfect because I took a terrible picture. So I think this is what the numbers are, but it's going to be close enough. 0.3419. So that's going to be my oxidation. That's going to be my reduction. So when we calculate E cell, it's always going to be the E of the reduction minus the E of the oxidation. So if we look at the two numbers, I'm just going to plug them into E cell. So I'm going to do 0.3419 because this part is my reduction, and I'm going to subtract a negative 0.4030 because that's my oxidation. When you subtract a negative, it becomes positive. So my E cell is going to equal 0.74. Now we rounded to 2 sig figs, obviously. So on the test tomorrow, you know, if you're a couple decimal places off, you know, based on rounding, that would be what we would get. But that's how you do number 16. All right, and number 7, and I'm finally done with this question. Number 7. Number 7 says, which reaction would create a better battery? So when you're trying to figure out which reaction would create a better battery, it's all about distance apart on the activity series and distance apart on the reduction potentials chart. So when you're trying to figure out which would make a better battery, the first thing you want to ask yourself is, will it be spontaneous? That's the very first question you want to ask yourself. And how you know if it will be spontaneous is if your solid piece is higher than your aqueous piece on the activity series. So if we look at, for example, the Li and the CO, I know that my Li is higher on the activity series than my cobalt is, so I know that will make a spontaneous reaction. In the second reaction, I've got I minus and Cr3 plus. So what I have to ask myself is, I don't have I minus on my activity series, so this is where I'm going to go to my reduction potentials chart. And I'm going to find my I minus and my Cr3 plus. So in this case, how the reaction is written, your 2I minus is oxidizing into I2, and your Cr3 plus is reducing into Cr. So when I go and I look at my reduction potentials chart, I find my iodine number, which is, oh, I can't read it again, lovely, positive 0.53 something, because I can't read the rest. And then I find my chromium number, which is negative 0.744. So what these numbers tell me, because I want this to be a battery, and battery means spontaneous, it means voltaic cell. So what this tells me is because my oxidation has a higher reduction potential than my reduction, is if I was to plug this into E cell, I would have a negative minus a positive, which would give me an overall negative E cell, which means this would not be a battery. Because in order for me to make a battery, I have to be able to create electricity. I have to be able to create positive voltage. And because when I do this reduction minus this oxidation, it ends up being a negative number, that would not actually make a battery at all. So this would not be a spontaneous battery. So question number one, reaction one, is the only one that would make a battery. Now let's just pretend that, so that's why this question, the answer is A for this question. Now let's just play hypothetical and let's play pretend that this second reaction actually was going to be spontaneous. So let's just pretend that this was going to be the reduction and this was going to be the oxidation. What you would want to do is you would want to actually calculate the E cell for both of your answers, and whatever one gives you the bigger voltage is going to be the one that makes the better battery. So first you want to ask yourself, will it be spontaneous? If one's spontaneous and one's not spontaneous, then the only one that would make a battery is the one that's spontaneous. If they're both spontaneous, then what you want to do is you want to calculate E cell, and the bigger voltage equals the better battery. All right, and I hope that helped you with number 7. So I'm going to go back to that Google Doc. Oop. I'm going to go back to that Google Doc now and kind of see if there's anything that I've answered or not answered at this point. Okay, so let's see here. So I did all those. Okay, I just answered this, so I'm going to call that at like 9. All right. All right, on the Google Doc, something I just addressed in this one was it's always anode minus cathode, always oxidation versus reduction on the on your calculation of E cell. So that always happens at oxidation minus reduction. All right, looks like that is all that kind of goes with that. So I'm going to move on to the next question. So it says, how do I know it's being oxidized and what's being reduced, like in number 1 on the back side of the review sheet under voltaic and electrolytic cells? So let's go ahead and get back to screen sharing my Word doc with you all. Alrighty, Rue. What did I just do? Is it screen sharing right now? Yeah, it is. Okay. Okay. All right, number 1 on the back side. Number 1 on the back side says draw voltaic cell between a compound composed of Zn, Zn2 plus, and Ni, Ni2 plus. Label Zn and Ni as anode and cathode. So what we have is we want to use either your activity series or your reduction potential chart. So Zn, Zn2 plus, and Ni, Ni2 plus. So either using your activity series or your reduction potentials, that's going to be what's going to drive for you which one's the anode and which one's the cathode. So if I use my reduction potentials, the reduction potential for zinc is negative 0.7618. This is number 1 on the back side under electrolytic. So volt/electro. All right, and nickel is, of course, when you want to find it, you can never find it, right? Negative 0.257. All right, so when you are using your reduction potentials to figure out what's anode and what's cathode, again, this is asking me for a voltaic cell. So in the voltaic cell, what I want to do is I want to have the number that's more positive be your reduction and the number that's more negative be your oxidation. So because these are both negative numbers, because this one is the more negative number, that means it does not want to happen as a reduction. It wants to happen as the oxidation. So this is what would oxidize, and this is what would reduce. So in this case, this would be our anode, and this would be our cathode. So you can use your reduction potentials chart to determine anode versus cathode. The other thing you can do is use your activity series. Zinc is higher than nickel at the activity series, so zinc has to be the anode, and nickel has to be the cathode. So those are the 2 ways you can go ahead and figure out which one is anode and which one is cathode. What's the purpose of spectator ions in an electrolytic cell? This one is going to be answered at 9:21. Okay, so the purpose of spectator ions in any cell, for that matter, the purpose of spectator ions in any sort of cell or electrolytic cell is going to be just simply to get whatever piece it is that we need for the oxidation or the reduction into the cell. So if we think of an electrolytic cell like what we did in class yesterday, so we did the, we did the electrolysis of copper sulfate. So if we think about what we had in that beaker, battery, positive, negative, over here, we had Cu2 plus and SO4 2 minus. Because we want to do the electrolysis of this solution, the whole purpose of this SO4 2 minus ion was to get the Cu2 plus ions just in the solution. I can't go to the scientific supply companies and ask for containers of just ions. They won't sell them to us. They only sell us ionic compounds or solid metals. So if I want to do electrolysis of a certain solution, I have to sometimes use those spectator ions to get the piece I need in there. So in this specific example, I wanted to reduce the copper at the cathode, and I wanted to oxidize water at the anode. So the purpose of using the CuSO4 solution was the fact that this SO4 2 minus is a non-reactive spectator. If I would have used something like copper chloride, the chloride would have actually oxidized before the water did. So I had to make sure that I chose a spectator ion that had a lower reactivity than the piece I actually wanted to react in my reaction. So it kind of serves two purposes. One, allowing us to get the piece that we wanted, in this case, to reduce in the solution. And then two, since the SO4 was less reactive than the water, it allowed the water to oxidize and make oxygen gas, which maybe I would need to fill a balloon to fly someplace, because that seems like a really efficient manner to get oxygen gas. So that's kind of the role of the spectators. Now, the other thing they do is they help kind of keep the solution overall neutral, because we know that when we do our redox reactions, one side of our solution typically takes on a positive character and the other side takes on a negative character. So keeping these spectator ions in the solution helps create an overall neutral solution as the reaction takes place. So that's the role of spectator ions in those solutions. And while we're at the same picture, I'm going to go ahead and pick up the next question, which is the purpose of a battery. All right, the purpose of a battery in an electrolytic cell is to drive the electrons. Electrolytic cells are non-spontaneous. So without the battery, we would not be able to make the electrons go the way we want them to go. Because we want, in this case, the water to oxidize and the copper ions to reduce. If we didn't have the battery and we put these electrodes into the solution, nothing would happen. We wouldn't get any solid copper forming anywhere, and we wouldn't get any bubbles of gas forming anywhere, because typically our copper ions would want to oxidize when they're compared to the water. So the battery drives the electron flow to make these things happen. By hooking up our inert electrode to the positive side of the battery, that forces electrons to be lost from this part of our electrolytic cell. So it drives the water to give up its electrons, even though it doesn't want to, by taking on a positive characteristic at this electrode. It then pumps out electrons to the cathode, which is going to give us an overall negative characteristic. And in this case, it's going to act like a big negative magnet that's going to suck in these copper ions to plate this electrode. So the whole purpose of the battery is it drives the electron flow to make something non-spontaneous occur. So these would not happen without that battery present. Okay. One thing I want to clarify, I just got a question in the Google Doc, going back into number 1 about, excuse me, how you know what's being oxidized and what's being reduced in a voltaic versus an electrolytic cell. When you're talking about a voltaic cell versus an electrolytic cell, oxidation always happens at the anode and reduction always happens at the cathode. So no matter what is occurring, what type of cell you have present, whether it's electrolytic with a battery or voltaic where you're just having spontaneous electron flow, you're always losing electrons at your anode and you're always gaining electrons at your cathode. So oxidation is always going to be the anode, reduction is always going to be the cathode. Where these things occur is driven by, do we want this to be spontaneous or do we want this to be non-spontaneous? So if we want this to be a spontaneous reaction where we're going to allow the electrons just to naturally flow how they want, when we look at our reduction potentials, the more negative number is going to be what gets oxidized. So in this case, if we wanted to make this a voltaic cell, we would have a zinc piece of metal as our anode, and we would have a nickel piece of anode as our cathode. And that would allow our electrons to be lost by the zinc and move over to the nickel for the reduction piece. No. Sorry, my dog was just eating something he shouldn't have been eating. Sorry about that. So again, in a voltaic cell, we would let the electrons naturally flow from the zinc, which has a lower electronegativity than the nickel. So the zinc would still oxidize at the anode and the nickel would still reduce at the cathode. If we were to make this thing as an electrolytic cell, because we know the zinc normally wants to be the anode, what we would do is we would make the zinc become the cathode. And because the nickel normally wants to become the cathode, we would make the nickel become the anode. And so when we hook it up to the battery, because the nickel would be hooked up to the positive side of the battery, the nickel would be losing its electrons to the battery, so the nickel would be oxidized. And because the zinc's hooked up to the negative side of the battery, the zinc would be taking in electrons, so it would be reduced. So oxidation and reduction always happen. Oxidation at the anode, reduction at the cathode. It's just where we put these metals is driven by, do we want the flow of electrons to be spontaneous, or do we want the flow of electrons to be non-spontaneous? All right, I hope that helps. I might have an awake baby right now. All right, I'm going to answer one more question real quick before I maybe take a quick break. And see if she goes back to sleep. So the next question is, does the distance of cells affect the overall potential difference? When you are making an electrolytic or voltaic cell, no matter what it is, the further apart your things are on the reduction potentials chart, the greater the voltage is going to be. So we're thinking about a spontaneous voltaic cell. If I have two metals that are really, really close to each other, they're not going to have a very significant electronegativity difference. So the electrons aren't going to really want to move that much between these two metals. So you're going to produce a very, very low voltage. Or if I choose something that is really, really high on the oxidation side and something that's really, really, really low on the reduction side, and I create two things that are very, very far apart from each other, I'm going to have something that really wants to lose electrons with something that's going to really want to gain electrons. So the electrons are going to whip really quickly from the oxidation to the reduction. So absolutely, the further apart your things are on the activity series of the reduction potential chart, the greater the voltage is going to be, because the difference between those two things, electronegativities, is really going to allow the electrons to be lost by the oxidation and gained by the reduction. So if you want to make a really awesome battery, you want to choose things that are really, really far apart, which is why we use lithium in things like cell phone batteries. All right, 9:30. Sounds like baby went back to sleep. So yay for us. We get to continue reviewing. And the next question we have in the Google Doc is, it says, in the book, a picture of an electrolytic cell is shown to have a salt bridge. However, we didn't use one in class. Is a salt bridge necessary? If so, what would we do? A salt bridge is definitely not necessary in an electrolytic cell. For that matter, we don't want you to think about electrolytic cells having salt bridges. We want you to think of electrolytic cells in this fashion, where it's just one container that does not have two solutions connected by a salt bridge. A lot of the times we see in the textbook the two solutions connected by the salt bridge is because we're talking about how electrolysis is a way to reverse electron flow. So in theory, it's how we recharge our batteries at night when we plug our cell phones in. So the reason it still has that salt bridge present is because it's talking about the recharging ability. So for your test, do not draw electrolytic cells with salt bridges. Draw them like this, where you've got a battery, one solution, two electrodes. Do not draw them with salt bridges. All right, looks like we got a lot of electrolysis questions. So I'm gonna keep on this track. All right, the next question is about the difference between electroplating and electrolysis in terms of half reactions. So I'm going to go ahead and I'm going to draw, excuse me, I'm going to draw the half reactions for this guy. So this is the thing that we did in class. So if we think about what's happening at the oxidation half reaction for this, and I promise I'll try and draw a little bit neater here. So what was occurring here is we were having water split into oxygen gas and H+ ions. Oh, no, not that. Not that. That's bad. I'm going to erase that too. That's not balanced anymore. Okay. So that was our oxidation half reaction, and this was our reduction half reaction. We had our copper 2+. So our half reactions showed that we had a separate reaction happening at the oxidation and a separate reaction happening at the reduction. So when you're doing an electrolytic cell like an electrolysis, you will always have two very different reactions. So they really won't be able to cancel that much out of one another. If we think about electroplating, so for example, the one that we did in class was electroplating a tin piece of, like a tin spoon with silver. This is my spoon, just so you know. I'm really good at drawing. So when we're doing electroplating, what our goal is to cover one metal with a different metal to either protect it or make it more attractive. So when we think about our main goal is to transfer these Ag metal atoms over to this tin. So we want to go ahead and we eventually want to get this Ag to cover that tin. How we do that is the Ag ions the Ag has to break out into Ag ions that can then travel to the tin electrode, because the electrons will be lost here at the anode. It's hooked up to the positive side of the battery, and they'll be gained here at the cathode, which is the negative side of the battery. So if we were to write half reactions for this electroplating, our oxidation half reaction would be our solid silver going to tin ions, going to silver ions and electrons. If we think about the reduction, we would have our tin ions plus electrons in the battery turn into solid tin. So when you look at combining these things, if I go to actually write an overall cell reaction, my silver would cancel, my tin ions would cancel, my electrons would cancel. So when you're doing electroplating, if you were to combine the two reactions, you would end up with nothing, because all we're doing is a transfer of solid from the anode to the cathode. So if you write your reactions correctly for an electroplating, you should not be able to combine them into an overall reaction, because everything should cancel. And I hope that helped with that guy there. Looks like I've got 2 more questions to go before I end. I've gone a little bit past my 9:10 time. You're lucky. I love you guys. It says the next question says, for the standard reduction potential, say Li plus E to Li has potential of negative 3.04. If you were to reverse it, okay. I want to talk about this right here. I'm talking to myself right now. Answer. Excuse me. I'm just going to copy and paste this into this doc here. I'll do that. Oh. Oh, that's not doing me any good. Good job, Etnyre. Okay, you're gonna have to wait for that to stop moving, because I'm amazing. I'm amazing. Okay, so here's the question we want to answer here. For the standard reduction potential, and they chose the lithium one, which is on top of the reduction potential charts, if you were to reverse this, would the potential still be negative 3.04 or positive 3.04? Whatever the number is in the book, copy it down exactly like it is. Never, ever, 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 ever change it. Because if we think about how we calculate E cell is your reduction minus your oxidation. So when you think about math, this negative sign means opposite of. So if I plug this into my E cell, I plug in a negative 3.04, the negative is going to flip it for me to make it positive. So when you're calculating E cell, do not change the numbers that you actually see on the textbook. Copy that number exactly how you see it on your test. But if you were to write the reaction, you would have to actually flip the reaction. So this is what you would want to do. You would want to flip that on your test, but do not change the number because the reaction for E cell will do it for you. So yes to flipping the reaction to show oxidation. No to flipping the number. No, E cell does it for you. Okay. And it looks like we are on to the very, very last question of the evening. Whoop. This is 9:37. All right, just double checking for writing oxidation numbers for polyatomic ions. It doesn't have to add up to 0, right? Yep, okay. Awesome. So this is a really easy question to end on, which makes me happy because my brain is like shot. Okay, so this question deals with ion charges for polyatomic ions. So if we had a polyatomic ion like PO4 that has a 3- charge, if you're doing the oxidation states for an individual polyatomic ion, your oxidation total has to equal the charge, not 0. So if we think about how to do this, this would be -2, which means we're -8 total, and I want it to equal -3. So if I make my P a +5, +5 minus 8 gives me that -3. Now, how this would look if we had like a compound, so let's say we had like Na3PO4, you'll see the P is still going to be +5. The rules about O is it's still -2. From our periodic table, we know Nas are +1s. So since it's an ionic compound here, it has to equal 0. +3 minus 8 means my P is still a 5. So where that +3 is going to come in to cancel out that -3 is from whatever positive piece you hook it up to in your problem. So if I'm asking you to do oxidation states for an individual polyatomic, make sure your total numbers equals the total charge. If it's a compound, make sure that you are overall neutrally charged. All right, and oh hi, I had to angle that differently so I could actually write. I think that is the last question that we have for the evening. So I hope that you guys found this helpful between Mrs. Staub and I splitting the time. Remember, we'll be in school tomorrow morning. If you guys do have more questions, you can always swing by and ask them for us in the morning. I'm hoping to be there as long as I'm feeling better. I will be there tomorrow, hopefully. And have a great night, guys. Study up. I know you're going to do awesome. Rock the test tomorrow. See ya.